When a Major League Baseball player throws a fastball, that ball's definitely got kinetic energy. We know that, because if you get in the way, it could do work on you. That's going to hurt. You got to watch out. But here's my question. Does the fact that most pitches, unless you're throwing a knuckleball, does the fact that most pitches head toward home plate with the baseball spinning mean that that ball has extra kinetic energy? Well, it does. And how do we figure that out? That's the goal for this video. How do we determine what the rotational kinetic energy is of an object? Well, if I was coming at this for the first time, my first guess, I'd say, okay, I know what regular kinetic energy looks like. The formula for regular kinetic energy is just 1/2 mv squared. So I'd say, all right, I want rotational kinetic energy. Let me just call that K rotational. And what is that going to be? Well, I know for objects that are rotating, the rotational equivalent of mass is moment of inertia. So I might guess, all right, instead of mass, I'd have moment of inertia. Because in Newton's second law for rotation, I know that instead of mass, there's moment of inertia. So maybe I replace that. And instead of speed squared, maybe, since I have something rotating, I'd have angular speed squared. And it turns out this works. So you can often derive, it's not really a derivation, you're just kind of guessing educatedly, but you can often get the formula for the rotational analog of some linear formula by just substituting the rotational analog for each of the variables. So if I replace mass with rotational mass, I get the moment of inertia. If I replace speed with rotational speed, I get the angular speed, and this is the correct formula. So in this video, we need to derive this because it's not really a derivation. We didn't really prove this. We just showed that it's plausible. How do we prove that this is the rotational kinetic energy of an object that's rotating like a baseball? Well, the first thing to recognize is that this rotational kinetic energy isn't really a new kind of kinetic energy. It's still just the same old regular kinetic energy for something that's rotating. And what I mean by that is this. So imagine this baseball that's rotating in a circle. Every point on that baseball is moving with some speed. So what I mean by that is this. So this point at the top here, imagine this little piece of leather right here. It's going to have some speed forward. I'm going to call this mass m1, that little piece of mass right there, and I'll call the speed of it v1. Similarly, this point on the leather right there, I'm going to call it m2. It's going to be moving down because this is rotating in a circle. So I'll call that V2. And points closer to the axis are going to be moving with smaller speed. So this point right here, we'll call it M3. Moving down with a speed V3, that is not as big as V2 or V1. You can't see that very well. I'll use a darker green. So this M3 right here, closer to the axis being right at this point in the center, closer to the axis, so its speed is smaller than points that are farther away from this axis. So you can see, this is kind of complicated. All points on this baseball are going to be moving with different speeds. So points over here that are really close to the axis, barely moving at all. I'll call this M4. And it would be moving at speed V4. What we mean by the rotational kinetic energy is really just all the regular kinetic energy these masses have about the center of mass of the baseball. So in other words, what we mean by K rotational is you just add up all of these energies. You'd have 1/2. This little piece of leather up here would have some kinetic energy. So you do 1/2 m1 v1 squared plus, and this m2 has some kinetic energy. Don't worry that it points downward. Downward doesn't matter for things that aren't vectors. This v gets squared. So kinetic energy is not a vector. So it doesn't matter that one velocity points down because this is just the speed. And similarly, you'd add up 1/2 m3 v3 squared, but you might be like, this is impossible. There's infinitely many points in this baseball. How am I ever going to do this? Well, something magical is about to happen. This is one of my favorite little derivations. It's short and sweet, because watch what happens. Ke rotational is really just the sum. If I add all these up, I can write it as a sum of all the 1/2 mv squareds of every point on this baseball. So imagine breaking this baseball up into very, very small pieces. Don't do it physically, but just think about it mentally. Just visualize considering very small pieces, particles of this baseball and how fast they're going. What I'm saying is that if you add all of that up, you get the total rotational kinetic energy. This looks impossible to do, but something magical is about to happen, and here's what we can do. We can rewrite. See, the problem here is V. All these points have a different speed, V. But we can use a trick that we love to use in physics. Instead of writing this as V, we're going to write V as, so remember that for things that are rotating, V is just R times omega. The radius, how far from the axis you are, times the angular velocity or the angular speed gives you the regular speed. This formula is really handy. So we're going to replace V with R omega, and this is going to give us R omega, and you still have to square it. And at this point, you're probably thinking like, this is even worse. What did we do this for? Well, watch. If we add this up, I'll have 1/2 m. I'm going to get an r squared and an omega squared. And the reason this is better is that even though every point on this baseball has a different speed v, they all have the same angular speed omega. That was what was good about these angular quantities, is that they're the same for every point on the baseball, no matter how far away you are from the axis. And since they're the same for every point, I can bring that out of the summation. So I can rewrite this summation and bring everything that's constant for all of the masses out of the summation. So I can write this as 1/2 times the summation of m times r squared, and end that quantity, end that summation, and just pull the omega squared out because it's the same for each term. I'm basically factoring this out of all of these terms in the summation. It's like up here, all of these have a 1/2. You can imagine factoring out a 1/2 and just writing this whole quantity as 1/2 times m1v1 squared plus m2v2 squared and so on. That's what I'm doing down here for the 1/2 and for the omega squared. So that's what was good about replacing v with r omega. The omega is the same for all of them. You can bring that out. And you might still be concerned. You might be like, well, we're still stuck with the m in here because you've got different m's at different points. And we're stuck with all these r squareds in here. All these points at the baseball are at different r's. They're all different points from the axis, different distances from the axis. So we can't bring those out. So now what do? Well, if you're clever, you recognize this term. This summation term is nothing but the total moment of inertia of the object. Remember that the moment of inertia of an object, we learned previously, is just mr squared. So the moment of inertia of a point mass is mr squared. And the moment of inertia of a bunch of point masses is the sum of all the mr squareds. And that's what we've got right here. This is just the moment of inertia of this baseball or whatever the object is. It doesn't even have to be of a particular shape. We're going to add all the mr squareds. That's always going to be the total moment of inertia. So what we found is that the k rotational is equal to 1/2 times this quantity, which is I, the moment of inertia, times omega squared. And that's the formula we got up here just by guessing, but it actually works. And this is why it works, because you always get this quantity down here, which is 1/2 I omega squared, no matter what the shape of the object is. So what this is telling you, what this quantity gives us is the total rotational kinetic energy of all the points on that mass about the center of mass. But here's what it doesn't give you. This term right here does not include the translational kinetic energy. So the fact that this baseball was flying through the air does not get incorporated by this formula. We didn't take into account the fact that this baseball was moving through the air. In other words, we didn't take into account that the actual center of mass of this baseball was translating through the air, but we can do that easily with this formula here. This is the translational kinetic energy. So sometimes instead of writing regular kinetic energy, now that we've got two, we should specify this is really translational kinetic energy. So we've got a formula for the translational kinetic energy, the energy something has due to the fact that the center of mass of that object is moving. And we have a formula that takes into account the fact that something can have kinetic energy due to its rotation. That's this k rotational. So if an object's rotating, it has rotational kinetic energy. If an object is translating, it has translational kinetic energy, i.e. if the center of mass is moving. And if the object is translating and it's rotating, then it would have both of these kinetic energies, both at the same time. And this is the beautiful thing. If an object is translating and rotating, and you want to find the total kinetic energy of the entire thing, you can just add these two terms up. If I just take the translational 1/2 mv squared, and this would then be the velocity of the center of mass. So you have to be careful. Let me make some room here. So let me get rid of all of this stuff here. If you take 1/2 m times the speed of the center of mass squared, you'll get the total translational kinetic energy of the baseball. And if we add to that the 1/2 I omega squared, so the omega about the center of mass, you'll get the total kinetic energy, both translational and rotational. So this is great. We can determine the total kinetic energy altogether, rotational motion, translational motion, from just taking these two terms added up. So what would an example of this be? Let's just get rid of all this. And let's say this baseball, someone pitched this thing, and the radar gun shows that this baseball was hurled through the air at 40 meters per second. So it's heading toward home plate at 40 meters per second. The center of mass of this baseball is going 40 meters per second toward home plate. But let's say it's also, someone really threw a fastball, and this thing's rotating with an angular velocity of 50 radians per second. And we know the mass of a baseball. I looked it up. The mass of a baseball is about 0.145 kilograms. And the radius of the baseball, so a radius of a baseball is around 7 centimeters. So in terms of meters, that would be 0.07 meters. So we can figure out what's the total kinetic energy. Well, there's going to be a rotational kinetic energy, and there's going to be a translational kinetic energy. The translational kinetic energy is going to be 1/2 the mass of the baseball times the center of mass speed of the baseball squared, which is going to give us 1/2. The mass of the baseball was 0.145, and the center of mass speed of the baseball is 40. That's how fast the center of mass of this baseball is traveling. And if we add that all up, we get 116 joules of regular translational kinetic energy. But how much rotational kinetic energy is there? So we're going to have rotational kinetic energy due to the fact that the baseball is also rotating. How much? Well, we're going to use 1/2 I omega squared. So I'm going to have 1/2. What's the I? Well, the baseball is a sphere. If you look up the moment of inertia of a sphere, because I don't want to have to do summation of all the mr squareds. If you do that using calculus, you get this formula. So that means in an algebra-based physics class, you just have to look this up. It's either in your book, in a chart or a table, or you could always look it up online. For a sphere, the moment of inertia is 2/5 mr squared. So in other words, 2/5 the mass of the baseball times the radius of the baseball squared. That's just I. That's the moment of inertia of a sphere. So we're assuming this baseball is a perfect sphere that's got uniform density. That's not completely true, but it's a pretty good approximation. And then we multiply by this omega squared, the angular speed squared. So what do we get? We're going to get 1/2 times 2/5. The mass of the baseball was 0.145. The radius of the baseball was about, what do we say, 0.07 meters. So that's 0.07 meters squared. And then finally we multiply by omega squared, and this omega was 50 radians per second. And we square it, which adds up to 0.355 joules. So hardly any of the energy of this baseball is in its rotation. Almost all of the energy is in the form of translational energy. That kind of makes sense. It's the fact that this baseball is hurtling toward home plate that's going to make it hurt if it hits you, as opposed to the fact that it was spinning when it hits you. That doesn't actually cause as much damage as the fact that this baseball's kinetic energy is mostly in the form of translational kinetic energy. But if you wanted the total kinetic energy of the baseball, you would add both of these terms up. K total would be the translational kinetic energy plus the rotational kinetic energy. So that means the total kinetic energy would just be 116 joules plus 0.355 joules, which gives us 116.355 joules. So recapping, if an object is both rotating and translating, you can find the translational kinetic energy using 1/2 m, the speed of the center of mass of that object squared, and you can find the rotational kinetic energy by using 1/2 I, the moment of inertia, for whatever shape it is. If it's a point mass going in a huge circle, you could use mr squared. If it's a sphere rotating about its center, you could use 2/5 mr squared. Cylinders are 1/2 mr squared. You can look these up in tables to figure out whatever the I is that you need, times the angular speed squared of the object about that center of mass. And if you add these two terms up, you get the total kinetic energy of that object.